Hello everyone! In this session we're going to cover polynomial division and the topic of factorization of cubics with the help of a scientific calculator on the condition that the cubic polynomials have an easy factorization. We start this session by reviewing polynomial long division. I'm going to assume that you have already studied this technique. However, if you haven't, I hope that you'll be able to learn the technique by watching this example. The technique that I'm going to demonstrate is very similar to integer long division. So, even for those of you who have not studied the technique before, it should look familiar. What we're going to do now is we're going to divide the dividend x cubed plus 2x squared plus 1. So the thing that we're dividing is called the dividend. And we're going to divide the dividend by the divisor x minus 1. What we're dividing by is called the divisor. So we're dividing the dividend x cubed plus 2x squared plus 1 by the divisor x minus 1. The first thing we do is we copy the dividend and we write it under the so-called division bracket. So here what you see here, this line is called a division bracket. So we write our dividend under the division bracket, and we write our divisor to the left of the division bracket. So here is the divisor, and here is our dividend. So here is our divisor. Alright. So here's the procedure that we're going to do. First, we identify the highest order term in the dividend, that is x cubed, and we identify the highest order term in the divisor, that would be x. And then we divide the highest order term, x cubed, by x. So the two terms we just found, we divide the highest order term of the dividend by the highest order term of the divisor. The output of this division operation, we're going to write it here where the question mark is located. Okay, so when we divide x cubed by x, we get, I'm sure you guessed it correctly, x squared. The next step is the following. We take the newly obtained term x squared and we multiply it by the divisor x minus 1. So we multiply x squared by the divisor x minus 1. The result that we get is, I'm sure you guessed it correctly, x cubed minus x squared. Next step. We take the dividend that we have, x cubed plus 2x squared plus 1, so we take that dividend, and from that we subtract the newly obtained intermediate polynomial. So that polynomial x cubed minus x squared that we obtained by taking x squared and multiplying by x minus 1. So that x cubed minus x squared, we subtract that polynomial from x cubed plus 2x squared plus 1. The result that we get is, I'm sure you guessed it correctly, 3x squared plus 1. Let's see why do we get 3x squared plus 1. I just want to make sure that we are all on the same page. So when I subtract from the dividend this polynomial, what do I get? Well, I'm having the polynomial x cubed plus 2x squared plus 1, and from that I'm subtracting the polynomial x cubed minus x squared. Since I'm subtracting two polynomials, the second polynomial must have parentheses around it. Alright, so what do I get? I get x cubed plus 2x squared plus 1 minus x cubed plus squared. Now minus with minus gives me plus. X cubed cancels. 2x squared plus x squared gives me 3x squared. And I have an extra 1. So indeed, x cubed plus 2x squared plus 1 minus x cubed minus x squared equals 3x squared plus 1. Now, what I just obtained, the polynomial 3x squared plus 1, that polynomial, I call it the new intermediate dividend. So I imagine that that newly obtained polynomial is my new dividend, and I repeat the exact same procedure that I did so far, with 3x squared plus 1 playing the role of the dividend. So I identify the highest order term, that is 3x squared, and I divide it by the highest order term of the divisor. So I divide 3x squared by x. I divide this guy by x. And the result that I get is, I'm sure you guessed it correctly, 3x. Alright, next step. The newly obtained 3x multiplied by the divisor x minus 1. And the result is, I'm sure you guessed it correctly, 3x squared minus 3x. Next, we subtract 3x squared minus 3x from the intermediate dividend 3x squared plus 1. Notice that we have two minuses in the play, a minus here and a minus there. So the result of our subtraction is, I'm sure you guessed it correctly, 3x plus 1. Once again, minus with minus gives me plus. Next, my new intermediate dividend 3x plus 1 has highest order term 3x. I need to divide 3x by the highest order term of the divisor. So I divide 3x by x to get, I'm sure you guessed it correctly, the number 3. Next, the newly produced number 3 I multiplied by the divisor x minus 1 to get, I'm sure you guessed it correctly, 3x minus 3. Next, I subtract the intermediate dividend 3x plus 1. From that, I subtract 3x minus 3. And the result is the number 4. Our division algorithm is complete. Let me explain why. If we were to continue this division process, on the next step, we would have to take the number 4 and divide it by the number x. So if we were to continue this process, here we would have to write as the next term 4 divided by x. However, 4 divided by x is not allowed because division by x exits the realm of polynomials, so that is not allowed by the algorithm. So we're supposed to stop our algorithm as soon as the next step in the algorithm would have to require the use of division by x. So here's where we stop. The so obtained expression, so these symbols that are written in this table here are called division tableau. So that would be the division tableau. Okay. Now, one thing I want to stress is that we have to be very careful when writing our division tableau. We have to make sure that terms are aligned properly. So all squares, so all second degree terms, must fall in the same column. All first degree terms must fall in the same column as well. If a polynomial is missing first degree terms, for example, the polynomial x cubed plus 2x squared is missing a linear term, a first degree term, well, you should imagine that you're having plus 0 times x here, and here you're having plus 0 times x, so you should imagine that the missing terms are added in there, and you should leave empty space for these missing terms. So you don't need to write 0 times x, but you should leave empty space. That is extremely important. So aligning terms properly in columns is going to make the difference between a properly filled in division tableau and a wrongly filled in division tableau. Once again, please make sure that you put all terms of like powers in the same column. So all second degree polynomial terms in one column, all third degree terms in one column, all 0 degree terms, or all constant terms in one column, and all linear terms in one column, leaving space, leaving empty space for missing terms. Okay, our division tableau is complete. Now, how do we read, how do we interpret our division tableau? What we see here, the number 4 is called the remainder. The polynomial that we see written here is called the quotient. And as we said, the number 4 here is called the remainder. So how is this interpreted? The polynomial tableau that we just filled in can be interpreted as the following equality between polynomials. The dividend x cubed plus 2x squared plus 1, so the dividend x cubed plus 2x squared plus 1, is equal to the quotient x squared plus 3x plus 3. That's the number that's the polynomial we just obtained here. So that one is the quotient, times the divisor x minus 1, the whole thing plus the remainder 4. So once again, the output of our polynomial long division is to be interpreted in the following way. The dividend equals the quotient times the divisor, the whole thing plus the remainder. In this example, I will teach you how to use polynomial long division to factor polynomials. Then I'm going to teach you how to use that to solve polynomial equations. Let us read the problem. Demonstrate that the cubic polynomial 6x cubed minus 19x squared plus 17x minus 3 is divisible by the linear polynomial 2x minus 3. Next, use your work to factor this cubic polynomial. And finally, solve the equation obtained by setting that cubic polynomial 6x cubed minus 19x squared plus 7x minus 3. Solve the equation obtained by setting that polynomial equal to 0. Now, what does it mean for one polynomial to be divisible by another polynomial? Two things. So one thing is divisible by another if, when we carry out the long division algorithm, in the end the remainder is 0. So saying that A is divisible by B, that is the same thing as saying, well, the remainder is 0. The remainder of what? Remainder of the polynomial division. remainder of the polynomial division algorithm. Of course, saying that a is divisible by b means that the remainder is 0 not only for polynomial division, it also means the same thing when talking about integer division. So a is divisible by b if the remainder of if a and b are both numbers, then a is divisible by b if the remainder of the integer division algorithm is 0. Okay. So we need to carry out a polynomial long division. Okay. So our dividend is 6x cubed minus 19x squared plus 17x minus 3, and our divisor is 2x minus 3. Okay, we identify the highest order term of the dividend, that is 6x cubed. We identify the highest order term of the divisor, 2x, and we divide one by the other. And we get, I'm sure you guessed it correctly, 3x squared. Next, identify the highest order term. Next, multiply 3x squared by 2x minus 3. And we get 6x cubed minus 9x squared. I'm sure you guessed it correctly. Next, subtract 6x cubed minus 9x squared from the dividend. So subtract the two polynomials that you see highlighted, and you get, I'm sure you guessed it correctly, minus 19x squared minus 9x squared equals negative 10x squared. So we get negative 10x squared plus 17x minus 3. Once again, minus 9x squared equals plus 9x squared. So in fact we are having minus 19x squared minus 9x squared, and that is minus 10x squared, what we wrote there. Okay. Next, we got our intermediate dividend, minus 10x squared plus 17x minus 3. We identified the highest order term in the intermediate dividend, that is minus 10x squared, and we divide it by the highest order term in the divisor. Minus 10x squared divided by 2x equals, I'm sure you guessed it correctly, negative 5x. Next, multiply negative 5x by 2x minus 3. The result is, I'm sure you guessed it correctly, minus 10x squared plus 15x. So once again, why do we get plus 15x? Because minus 5x times minus 3 equals minus times minus is plus, so that equals plus 15x. Okay, now let us subtract minus 10x squared plus 15x from the intermediate dividend, and we get, I'm sure you guessed it correctly, 2x minus 3. Again, we identify the highest order term, that is 2x, divided by the highest order term in the divisor, 2x, to get, I'm sure you guessed it correctly, 1. Finally, we multiply 1 by 2x minus 3 to get 2x minus 3. We subtract the two polynomials to get 0. 0 is of degree smaller than the degree of the divisor, so our division algorithm terminates here. Just a reminder, this here is the quotient of our polynomial long division, and this here is the remainder. So this is the remainder of our polynomial division. As promised, the remainder of our polynomial long division is 0. How was that promised? Well, we were promised that the dividend is divisible by 2x minus 3, which, as we said, means that we were promised that the remainder is 0. Okay. So now, let's see how that polynomial long division helps us factor the cubic. As we remember, the interpretation of the polynomial long division was the following. The dividend equals the quotient, so that is the quotient here, right? So this is the quotient here. So the dividend equals the quotient 3x squared minus 5x plus 1 times the divisor 2x minus 3 plus the remainder. But the remainder happens to be 0. So the dividend is the quotient times the divisor plus the remainder 0. But we were lucky and the remainder was 0. So 0 can be omitted. So we were lucky and we got no remainder. So because of that, we have in fact achieved a factorization of our cubic, right? We have managed to represent our dividend as the product of the quotient and the divisor. Once again, that happens only by the luck of the remainder being 0. So we have in fact factored out our dividend as 3x squared minus 5x plus 1 times 2x minus 3. So we have managed to factor our cubic. Now, our work is not complete. We're done with the polynomial long division, but we have not yet fully factored the cubic. So let's do that. Let's fully factor the cubic. What remains to fully factor the cubic? Well, we need to factor the quadratic 3x squared minus 5x plus 1. We need to factor that expression here. Now, this is a quadratic and we know everything about quadratic factorization. This quadratic doesn't have any easy roots. You can try yourself the divisors of 1 and you'll find out that they don't really work. So since there is no easy factorization of that quadratic, 3x squared minus 5x plus 1, we are going to use the quadratic formula. So the two roots are, well, two roots of a quadratic equation are given by the formula minus b plus or minus radical of b squared minus 4ac over 2a. So the number a equals 3. Number a equals 3. The number b equals negative 5. So the number b equals negative 5. And the number c equals 1. C is equal to 1. So we got our roots. Let's see how that simplifies. Here we get negative 5, that is 5, plus or minus a radical of 25 minus 4 times 3 is 12, the whole thing over 6, so we get 5 plus or minus radical of 13 over 6. 5 plus or minus radical of 13 over 6. So our two roots are 5 plus radical of 13 over 6 and 5 minus radical of 13 over 6. Say this is the root x1 and this is the root x2. So our factorization is complete. We factored our quadratic 3x squared minus 5x plus 1 into a product of two linear terms, x minus x1 and x minus x2. Now our cubic is fully factored into linear terms and we are done with the factorization. So we have fully factored our cubic. We're almost done with the problem. We have one more thing to do. We need to solve the equation obtained by setting the polynomial we just factored equal to 0. Okay, so 6x cubed minus 19x squared plus 17x minus 3 equals 0. Now we already have a factorization, so let's use it. We get that 3 times x minus 5 plus radical of 13 over 6, double close parenthesis, times open parenthesis x minus open parenthesis 5 minus radical of 13 over 6 double close parenthesis times 2x minus 3 equals 0. Okay, now that means we're having a product of three numbers that is 0. That means that one of those three numbers must be 0 or more, but of course they can't all simultaneously be 0 because they're different numbers. So that means that either 2x minus 3 is 0, or x minus 5 plus radical of 13 over 6 is 0, which means that x is equal to 5 plus radical of 13 over 6, or x minus 5 minus radical of 13 over 6 is 0, which means that x is equal to 5 minus radical of 13 over 6. We're almost done. We only need to solve this equation. 2x minus 3 equals 0. That is very easy to solve. That's a linear equation. And we see that x equals 3 over 2. So our solution in this example, we're asked to solve a cubic equation. The equation is 2x cubed plus x squared minus 7x minus 6 equals 0. Now, solving general cubic equations is difficult. It requires something called Cardano's formula. And that problem is too difficult for most exams. However, there are additional things that this problem asks us to do. The problem asks us to plot the cubic with a graphing calculator. This suggests that maybe our graphing calculator, the plot of our graphing calculator, will help us solve the equation in some way. So let us use our graphing device to plot 2x cubed plus x squared minus 7x minus 6. Now, please try to plot that on your graphing device right now. Please use the same graphic device you plan on taking with you to your exams. The resulting plot should look something like this. Alright, next. The graph appears to intersect the x-axis at 3 points. I don't know if you see where those points are, but here's one point. Here's another point. And here's a third point. So here's where the graph intersects the x-axis. These are the three solutions we're seeking to find. So the graph appears to intersect the x-axis where? Well, this number here looks like the number 2. This number here looks like the number -1. And this appears to be halfway between -1 and -2. But it's difficult to tell for sure. But one could guess with some certainty that the three intersections are at -1.5. So this point here, -1.5, -1, this point, and 2. This means that this left-hand side that we see here, if our guess for the numbers, for the three numbers, why am I saying the word guess? Well, because we eyeballed these numbers. We just looked at the graph, and it looks like the graph passes through the exact pixel that it should pass through, but maybe our eyes deceive us, right? So especially on if you plot this with a small on a small calculator screen, it is very possible that due to the size of the screen your eyes will deceive you, or that the scale of your calculator will not be fine enough. That may happen. So at the moment it seems that we have guessed the solutions correctly, but our eyes may be deceiving us. Anyways, provided that our eyes are not deceiving us, the left hand side should factor as well. It should factor as x minus x1 times x minus x2 times x minus x3, where x1, x2 and x3 are the three roots. This is x1, this is x2 and this is x3. Actually, the left hand side should factor as the leading coefficient a0 times x minus x1 times x minus x2 times x minus x3. So the left hand side should factor as 2 times x minus x1 times x minus x2 times x minus x3. So it seems that our eyes are not deceiving us. It seems that we have correctly eyeballed the factorization. But how can we be sure? Maybe our graphic device just is deceiving us, and maybe the graph, if we zoom, will not pass to the points minus 1.5, minus 1 and 2. Well, we do not need to rely on our eyes alone. What we can do is we can take that factorization and uncover the parentheses. If our guess were correct, when we uncover the parentheses, we should get the original polynomial 2x cubed plus x squared minus 7x minus 6. So in this way, we can I must admit that in the beginning we guessed this factorization, right? So this factorization wasn't guaranteed to be so, but we can verify that our guess is correct with absolute certainty. So there's no guesswork involved once we verify our answer. So yes, the graph did help us for some educated guess, but we're absolutely certain that if we uncover the parentheses and we get what we want to get, the original polynomial, we're guaranteed that this factorization is the correct one. So let's uncover the parentheses. First, minus with minus. So x minus minus 1.5 is x plus 1.5. X minus minus 1 is x plus 1. And just a reminder, in order to not have to deal with decimal numbers, I'm going to take the number 2 and I'm going to distribute it inside the parentheses. So I'm going to have 2 times x plus 1.5. That's what I'm having here. And I'm going to simplify that as 2x plus 2 times 1.5. So I'm going to simplify that as 2x plus 3. That is what I have written here. Okay, so what I have done is I have simplified this block to this block, so that I didn't. So I did that simplification, so I don't need to deal with decimals. I don't need to deal with the decimal 1.5. When I distributed the 2, the decimal 1.5 became the integer 3, which is much easier to work with. Alright, next, I'm going to uncover parentheses. What am I going to do? So I'm going to take those two parentheses, 2x plus 3 times x plus 1, and I'm going to distribute them. So 2x times x equals 2x squared. Next, the outer terms. 2x times 1 is 2x, and 3 times x, the inner terms, is 3x. So 2x plus 3x equals 5x. Next, 3 times 1 equals 3. So here I had 2 times 2, so 4 summands. Here I have written 3 summands. However, if you recall, when I uncovered the parentheses, I combined 2x plus 3x to 5x. So here I wrote 5x, which is obtained by taking 2x plus 3x. Alright, so our check works out. We expect 4 summands here, but we are having 3 because we combined two of these 4 summands into a single one. Alright, next I copy x minus 2. Alright, now let us distribute further. 2x squared plus 5x plus 3 times x equals 2x cubed plus 5x squared plus 3x. And 2 times 2x squared is 4x squared, 2 times 5x is 10x, and 2 times 3 is 6. And I have also copied the negative sign here. Please do not forget the parentheses. Okay. Next, I'm ready to combine. I copy 2x cubed here. Next, 5x squared minus 4x squared equals x squared. 3x minus, please pay attention, there is a minus in here. So 3x minus 10x is negative 7. And finally, I have minus 6. Please do not forget the minus. Okay. So let's take a look. 2x cubed plus x squared minus 7x minus 6 is exactly equal to the cubic that we wanted factor. So our factorization, our eyeballing is correct. Okay. So we have not been deceived by our graphing device. We have indeed written a perfect factorization for our cubic. So our cubic 2x squared plus x squared minus 7x minus 6 factors is 2x plus 3 times x plus 1 times x minus 2. And that being equal to 0 corresponds to either x equal to negative 3/2. Just a reminder, negative 3/2 is minus 1.5. Or x equal to negative 1. Or x equal to 2. And that negative 3/2 in here is this one. Alright, our solution is complete. By the way, notice that the bulk of the work in this problem consisted in verifying that the original solutions that we eyeballed were correct. So if I were to blindly trust my graphing device, I could have immediately told you that 2x squared plus x squared minus 7x minus 6 factors like this, and I could have immediately told you that these are the 3 roots. In fact, I wouldn't have even needed to factor it. I could have immediately told you that minus 3/2, negative 1 and 2 are the roots without going through the factorization. However, the intermediate factorization was a tool for verifying that our graphing device has not deceived us, and that is quite important, right? We want to be sure that our solutions are correct. This example again asks us to solve a cubic equation. Again, the example asks us to use our graphic calculator as an aid to our computation. However, as we're going to see, this problem is going to be quite different from the preceding one, despite the fact that the two look very similar. Once again, please do not forget to exercise yourself in plotting graphs of functions with the device you're going to bring at your exam. So here's approximately what you should get when you plot the function with your graphing device. Okay. Next. It seems that the graph of x cubed minus x squared minus 8x plus 6 intersects the x-axis in 3 points. Here, here, and here. So the graph of our function intersects the x-axis at 3 points. Now, can we eyeball those 3 points? Well, in fact, that's a trick question. Sure, I see the number 3. I see that the graph of the function intersects the x-axis at the number 3. I can see that one. But the other two, I really can't figure them out from the picture. I see that this number here is close to -3, but not exactly equal to -3, and I see that that number there is close to 1, but not exactly equal to 1. So where exactly what are exactly the values of these two numbers? Well, I cannot eyeball them at this resolution, and quite frankly, if you're using a graphing device, you may have difficulty with your graphing device as well. Okay, so it seems that pure guessing here will not quite work. However, we are armed with the technique of polynomial long division, and we remember that we can use polynomial long division to factor polynomials. Let's do exactly that. So in order to find out what are the two roots besides 3, here's what we're going to do. We're going to take the original polynomial x cubed minus x squared minus 8x plus 6, and we're going to divide it by x minus 3. So we guessed that 3 is a root. If 3 is a root of a polynomial, that means that that polynomial is divisible by x minus the root, right? So if 3 is the root x1, then we're guaranteed that x cubed minus x squared minus 8x plus 6 will be divisible by x minus x1, by x minus 3. So if our guess here is correct, we're guaranteed that the original polynomial will be divisible by x minus 3. Now, how will we know whether the dividend is divisible by x minus 3? We will know if the remainder turns out to be 0. If the remainder does not turn out to be 0, that means that our eyes have deceived us and 3 is not a root. However, if our eyes have not deceived us, then dividing that polynomial by x minus 3 should yield us a remainder 0. So our division serves a twofold purpose. First, to verify that our eyes are not deceiving us, and second, to aid us with factoring x cubed minus 8 squared minus 8x plus 6. Alright, now we're heavily trained on polynomial long division. We did that a few examples ago. So I'll proceed relatively quickly. First, identify the leading term in the dividend and the leading term in the divisor. So next, divide the two leading terms. X cubed divided by x equals, I'm sure you guessed it, x squared. Next, multiply x squared by x minus 3 to get, I'm sure you guessed it, x cubed minus 3x squared. Next, subtract the dividend and the new intermediate to get, I'm sure you guessed it, so minus x squared minus 3x squared equals 2x squared minus 8x plus 6. So 2x squared minus 8x plus 6. Next, identify the leading term in the new intermediate dividend, so 2x squared. Divide 2x squared by x to get, sure you guessed it, 2x. Next, 2x times x minus 3 equals, I'm sure you guessed it, 2x squared minus 6x. Next, subtract 2x squared minus 6x from the intermediate dividend 2x squared minus 8x plus 6 to get negative 8x minus 6x equals negative 2x plus 6. So I'm sure you guessed it, negative 2x plus 6. Finally, take negative 2x divided by x to get, I'm sure you guessed it, negative 2. Negative 2 times x minus 3 equals negative 2x plus 6. Finally, we subtract the remaining two polynomials to get remainder 0. 0 is our remainder. And indeed, the original cubic x cubed minus x squared minus 8x plus 6 is divisible by x minus 3, and x equals 3 is indeed a root of that cubic. Okay, so our quotient is x squared plus 2x minus 2. So, a reminder, this polynomial here is equal to the quotient times the divisor plus the remainder. Right, and the remainder is 0. So that's our remainder here. So x cubed minus x squared minus 8x plus 6 is equal to x minus 3 times x squared plus 2x minus 2 plus 0. Alright. We can remove the plus 0. So we have in fact factored our cubic. Alright. So we know from our cubic factorization that either x minus 3 equals 0, that corresponds of course to x equals 3, or that we are getting x from this equation, x squared plus 2x minus 2 equals 0. So either x is equal to 3, we already knew that, we already eyeballed the solution x equals 3, or x is equal to, now this quadratic here, x squared plus 2x minus 2, does not have any easy solutions. So we're going to use the quadratic formula. The quadratic formula says that this quadratic here yields us two solutions. Minus b plus or minus radical of b squared minus 4ac divided by 2a. So a equals 1. So I'm using the quadratic formula. Here a equals 1. This is my a. Next b is equal to 2. And finally c is equal to negative 2. This is my c. So this is a equals 1, b equals 2, and c equals negative 2. So this is b, this is a, and this is c. Okay, just a reminder, our formula for the quadratic equation was x equals negative b plus or minus radical of b squared minus 4ac over 2a. Alright, that's the formula we used above. Alright, now we're ready to simplify. Let's see, we're having negative 2 plus or minus radical of 4 minus minus, minus minus is plus, so plus 8 divided by 2, so we get minus 2 plus or minus radical of 12 over 2. So we get minus 2 plus or minus radical of 12 over 2. That can be simplified a little bit further. So I can simplify a radical of 12 like this. Radical of 12 equals radical of 4 times 3, which equals radical of 4 times radical of 3, which equals 2 times radical of 3. So radical of 12 I can replace with 2 times radical of 3. So I replaced radical of 12 with 2 times radical of 3. And here, as you can see, I'm having a common factor of 2 which repeats top and bottom. So I can simplify further like this. That I can simplify I can factor out 2 to get negative 1 plus or minus radical of 3, the whole thing over 2. The 2 cancels top and bottom, and I get negative 1 plus or minus radical of 3. And this is our final solution. So finally we get our final answer: x is equal to 3, or x equals negative 1 minus radical of 3, or x equals negative 1 plus radical of 3. So here are our 3 solutions. Now, as you can see, it wouldn't have been very easy to guess that this number here is exactly equal to negative 1 minus radical of 3. That is not something that I could easily eyeball from the graph of this function. So to recap, in order to solve this problem, we used our graphing device to guess one of the roots. Then we used polynomial division in order to factor the cubic. And finally, we used the quadratic formula with a relatively nasty answer to solve the remaining quadratic after our initial factorization. This is our final example of solving cubics with the aid of a graphing calculator. This example is going to turn out a little bit different from the preceding 2 examples. Let's see in what way. First, we need to plot our cubic. So we're trying to solve the equation 2x cubed plus x squared plus 5x minus 3 equals 0. And our first step is, as requested by the problem, our first step is to plot that cubic. So using our graphing device, please don't forget to bring the device you will use on your exams. So using our graphing device, we should get a plot similar to this one. Okay, so here's the plot that we get. Now we immediately notice that there's something different with this problem compared to the other problems. We notice that the graph of our cubic appears to intersect the x-axis at only one point. So I can see only one intersection, not 3 intersections as we saw in the preceding cases. So perhaps this cubic equation has only one real solution. That's option number 1. Or maybe it has other solutions, but they're very far away. Maybe that cubic goes up and then goes back down and intersects the x-axis, but we did not choose the viewing window properly. So what's going on? Well, we don't know. Let's see how we can check whether this cubic has one or more real solutions. Okay, on this picture we see only one root. Now, can we eyeball that root? Now, here it seems that I need to zoom in. So, need zoom. Now, when using your own graphic calculator, you may run into the same problem, that it is difficult to see where exactly the graph of your function intersects the x-axis. I'm going to try, I'm going to imitate the situation of a real graphing calculator, and I'm going to ask you to guess the value of the intersection here without being able to zoom. That's likely going to be your situation in an exam setting. You may not even have time to zoom in to see where the graph of your function intersects the x-axis. So, what is the root that you see? Well, it seems that the point here is exactly halfway between 0 and 1. So it seems that this number here is 0.5. Okay, so that's our guess. We guess that the only root that we can see is x equal to 0.5 or x equal to 1/2. Now, here, because of our issues, it was difficult. The picture was not zoomed in at a good enough resolution. Actually, this guess we're not very certain of it. So we really want to verify that x equal to 1/2 is indeed a solution. So our first task is to actually verify that x equal to 1/2 is a good guess. Our second task is to check whether there are other roots, maybe far away from 0. We don't see them, but maybe somewhere far away there are more roots that we have, and we simply haven't plotted far enough. Okay. So what we're going to do, since we can see the root x equal to 1/2, we're going to use that to factor our cubic. So here's our cubic, 2x squared plus x squared plus 5x minus 3, and I'm going to divide that cubic by x minus 1/2. Once again, I'm dividing by x minus x1. Here's the number, here's the root x1 that I'm seeing with my eyes. Now, if I saw the numerical value of x1 correctly, so if the root is indeed equal to x1, then the polynomial division here will yield the remainder 0. If I do not get remainder 0, I eyeballed the solution wrongly, and I should try some other technique. Okay, but of course this problem is, well, let's see what's going on. Okay, so now I'm going to proceed quickly. The leading term in the dividend is 2x cubed divided by x to get, sure you guessed it correctly, 2x squared. Next, multiply 2x squared by x minus 1/2 to get 2x cubed minus x squared. Next, subtract from the dividend the 2x cubed minus x squared to get 2x cubed cancels, and x squared minus x squared equals 2x squared. So we get 2x squared plus 5x minus 3. Next, identify the highest order term in the intermediate dividend. That's 2x squared. 2x squared divided by x is, I'm sure you guessed it correctly, 2x. Next, 2x times x minus 1/2 is, I'm sure you guessed it correctly, 2x squared minus x. Now, we subtract from the intermediate dividend 2x squared minus x to get, I'm sure you guessed it correctly, 5x minus x is 6x, so we get 6x minus 3. Finally, 6x divided by x is 6. 6 times x minus 1/2 is 6x minus 3. Finally, subtract the 2 to get remainder 0. Indeed, we got a remainder 0, exactly as we wanted. So our guess that 1/2 was a root of our cubic is correct, because when I divided the dividend by the divisor, I got a remainder 0. Now, our quotient is 2x squared plus 2x plus 6. So that means that my cubic, 2x cubed plus x squared plus 5x minus 3, equals the divisor, x minus 1/2, times the quotient, 2x squared plus 2x plus 6, plus the remainder 0. That is our remainder 0 here. Alright, of course we can omit the plus 0. So in this way, we have factored our cubic. We have factored 2x cubed plus x squared plus 5x minus 3 into x minus 1/2 times 2x squared plus 2x plus 6. So, the product of two numbers is 0, hence either x minus 1/2 is 0, or 2x squared plus 2x plus 6 is equal to 0. So if x minus a half equals 0, that means that x is equal to 1/2. This was the solution that we had already seen from the graph. Next, in order to solve the equation 2x squared plus 2x plus 6 equals 0, so in order to solve this equation, 2x squared plus 2x plus 6 equal to 0, right? That's our other option. We can simply use the quadratic formula. So the solutions are, let's see, we can use the quadratic formula. This is A, this is B, this is A, this is B, and this is C. And this here is C. This is A, this is B here, and this is C. Just a reminder, the quadratic formula said that x equals negative b plus or minus radical of b squared minus 4ac over 2a. So b is negative 2. Oops, that's negative. Well, that's b squared here, right? And a is 2 and c is 6. All right. So that's what we get, and so we get negative 2 plus or minus radical of 2 squared is 4. 4 times 2 times 6 is 8 times 6, which is 48. Whole thing divided by 4. 4 minus 48 is negative 44. Whole thing divided by 4. So we get negative 2 plus or minus radical of negative 44 over 2 times 2. Now, we got the radical of a negative number. So that is complex. So this is complex, not real. Now notice that the problem asks us to find all real solutions of the equation. So complex numbers are excluded. So no real. So on this side of our equation, we should write no real solution. Once again, there are complex solutions, namely negative 2 plus or minus radical of negative 44 over 4. So there are complex solutions, but the problem specifically asks us for real solutions. Okay, so on this branch of our solution, we write no real solution. So in this way, we have demonstrated that x equal to 1/2 is the only real solution. Our solution is complete, and our answer is x equal to 1/2.